So I have to thank organizers again for the records. And now there were several about jets, but to be self-consistent, I will briefly go through this. So JL will be the just bundle, okay, over M, and well, if it's just written like this, it's space of jet of functions from U to M, but more generally, you can think about jets of sections of bundles, of bundle pi, then you will have a bit more coordinates. So presently, I would like to do exposition just for the simplest jet space, but it's easy to upgrade. So if you choose coordinate system xi on a manifold M, then it automatically induces coordinates on jet bundle. So xi and u alpha, where u alpha stands for kind of derivative at the point x. So that's just a coefficient of the Taylor decomposition. And alpha throughout will denote the multi-index, and the length will be up to L if you talk about L jet space. And the first important thing to notice is that when we do forgetful projection from L jets to L-1 jet, it's actually a fine bundle. Okay, and so the affine fiber is modeled on vector space, which is L symmetric power of cotangent bundle of cotangent space at a given point. Okay, and that's kind of important actually for what happens later. And just to understand it informally, you take Taylor series expansion of a function and you take the top terms. That's precisely will be coordinates on this SL T star. Okay, and when we go to infinite jets, where it's just projective limit because we have this bundle of projections. So when we go going back, we pick up actually the infinite decomposition. And the space of function of it, it's actually injective limit on the space of functions of finite jets because it's embedded now. So any function on infinite jet actually depends on finitely many arguments. Okay, and the infinite jet is much simpler in a sense because every jet space has a so-called Cartan distribution. However, for finite jets, the Cartan distribution is actually non-integrable because it has a vertical part and commutator of vertical and horizontal part actually give you bigger and bigger distribution, which fills the entire space. When you go to infinity, the vertical part actually smashes to nothing, and you leave only horizontal, which is integrable, and that's flat connection. And if you'd like to define this flat connection, then it's here. Here's the lift. If you take vector field on the base, okay, then you just differentiate any function along, and this gives you actually derivation of functions, and which is a vector field, but now in infinite jets. This can be written as follows in the formula below. So, well, if you take any functional jets and you differentiate it, and then restrict to jet lift of any function, it's the same if you first take the function, restrict it to any jet, right? Then you get a function on the bundle on the base, and then differentiate. Okay, and if you'd like to see formulas and coordinates, that's actually simple. So if x is AI di summation, where a is actually coordinates on the base, then here's the lift. Dx will be AI di, where di is total derivative. And that's infinite summation, and that's the formulas. And this I and alpha is just you add I to multi-index alpha, it becomes one by one longer. Okay, and in general, operators total derivatives will have the same form, but now coefficient can depend on jets, unrestricted. Okay, so then if you talk about scalar differential operator of order less equals than n, and non-linear operator in general, right? So it's just actually a function on jets. I can write both infinities like C infinity, J infinity, or I can just say it's on certain jet space. Also, choice C infinity for function is not mandatory. There's also possibility to vary it. We can talk about analytic or rational functions, and this will show up later. Also important to vary this. Okay, so we have this function, then, well, it can be actually not one function, but several functions. So we define PDE system. Just put locus, and prolongations given by actually differential ideal. It will be a left ideal. We can multiply this non-linear operator from the left by operators and total derivatives, so-called C differential ideal in the theory. Okay, so you basically just derive all possible corollaries, differential corollaries of this, and if you restrict up to certain order, well, that's the prolongation of order K. Okay, then you get geometrically submanifolds and jets K plus L, and you can go to projective limit again and get infinite prolonged equation. Okay, so maybe in order not to write this prolongation symbol, sometimes it's also convenient to write EK, just to know that that's submanifolds and K jets. So when K greater equals an L, that comes with restrictions, but also convenient to take K less than L, then there's no restrictions, entire jet space. Okay, a couple of terminologies. The equation is called compatible or formally integrable sometimes, if every projection is a submersion. Okay, and this tells you that you get no compatibility conditions. Equation is called consistent or formally solvable if actually you have a solution at any point. So you have projection to the basis is actually submersion. This terminology changes from field to field. Some people say consistent for compatible and so forth. There's a small chaos around, but okay, at least I will keep this definition. Okay, and also people say involutive, but it's even more restrictive. I will come to this a bit later. Yeah, sure.
What happens with these definitions when you're dealing with a system with non-trivial differential consequences, where you differentiate your equation and obtain the equation that has
lower order?
You have
so system is non-compatible. Very good question. I'll answer in a couple of slides. If we are able to arrive to E infinity, and this is either finite dimensional or actually analytic, then by either Cauchy-Kovalevsky, Cartan, Keller, well, depending on what you like, theorem. Well, basically, like Cartan Keller is a finite combination of Cauchy-Kovalevsky theorems, right? So then there are solutions to the system. That's also true in some other contexts, but I don't want to go there. If you assume certain ellipticity, then that's also true. Okay, okay, so for a moment, let's assume compatibility and assume that doing some prolongation, we don't get anything new. The projection is actually isomorphism, diffeomorphism. Okay, if this happens for one index, then it actually happens for all indices above it, and I call it F-like final. And the prolongation is stabilized, and equation will be of finite type. In this case, E infinity is actually finite dimensional. So in this case, okay, just briefly to relate to what happens. So Cartan distribution on J infinity induces a distribution on equation just by intersections. Well, it will be horizontal of the same rank, actually, which equal dimension of a manifold. And since it was flat ambient, it's also flat here. Okay, so we get actually foliation. It's foliation by solutions. And solutions can be just identified as parallel sections of this bundle. Well, if bundle is linear, the equation is linear, then it's just linear connection.
Not really foliation of every one deep essence of one point. Not really foliation.
No, it's finite type. So it's a finite type, right? So in this case, this analyticity and also like uniqueness you have. Yeah, okay. So, and we can just view it as a local quotient by the foliation, E by the CE, and this will be identified with solution space, which is kind of a defined solution with this Cauchy data. It's pretty local construction here. Okay, and hence, finding solution for PDE system is actually, in this case, reduced to ODEs. It's kind of known that basically you get reduced integration of Frobenius distribution. Yes, so that's the question about ODEs. It doesn't mean that you completely solve the problem. However, if you have some symmetry group staying behind, this is inherited, and this can help you solve ODE. For example, if this group is solvable acting transitively to this distribution, then this thing can be integrated in quadratures. Okay, so that's this case, but I started with assuming compatibility here, so everything is nice, like you don't have any intermediate problem. So let's bypass this. Let's not make this assumption, and however, let's still think that up to a certain point you have submersion, right? So you don't have compatibility conditions for a range of indexes from L to F. So you can freely do prolongation, okay? And then assume that this F is the same as before, where actually you have isomorphism is the next prolongation or possible isomorphism. But the important thing that for Cartan distribution on finite jets, which is just intersection of Cartan distribution and jets with equation, it will be completely horizontal again in this case. So it is a connection, right? So if equation was linear, it's linear connection, otherwise it's just general connection. And then, of course, if you had some symmetry in the problem, that's, I don't know, or it can be called case in some case group. So then it gives you a way to describe all possible connections. So of course you can also add lower the term so-called curvature corrections. Okay, so this connection is something like resemble what people talk about tractor connection, and in fact in the corresponding context like parabolic geometry, yes, it can be identified with those, but in principle that's more general. That's more general story. Of course, here are some, but this assumption which I made from the beginning that you can go up to the level system becomes actually finite type. Well, it's finite type from the beginning, but when you arrive at the symbol actually becomes trivial, and you don't get any compatibility conditions. That's not a general situation. There are systems for which you get compatibility actually before you arrive to Frobenius type, and yes, you have to be able to treat those compatibilities.
But it's a question. So, but this way, this connection is flat. And if you
No. It was flat on the previous slide when I assumed compatibility. Here it's actually not. It's just a connection. And actually, that's where
it's the way to get the curve back.
Yes. Okay. So in this case, of course, since there are actually curvature, so you can't expect solution passing through any point, and then naturally, of course, even this right-hand side, this quotient is not actually well defined. So because you have to complete your distribution to integrable one and then do quotient, so solution space actually decreases. Okay, but at least it's clear what to do in this case because you get Frobenius condition, and basically what you do, your compatibility in this case is just you check cross derivatives. Okay, in general context, compatibility can be more complicated. It's not necessarily like uses pair of equations, or what we call cross differentiations. It can be more complicated differential syzygies. Several equations at once. Okay, and it's the same as in tractor for tractor connection. This is in the linear context, for example. Okay, so that's kind of the general start. Let me now give an example. So consider metric. Yeah.
May I ask a quick question? If you go back one slide, if you go to tractors which are more complicated than standard tractors, then usually so
but you may need to do modification of your tractor connection, and you I just showed.
So you get something like the correlation.
Well, just comes natural resolution. Just base, dimensional base. Just a set a manifold, take Riemannian metric on it, and well, see the Riemannian doesn't matter. Then define Hamiltonian, right, by inverting the metric, because, yeah, so here's the formula, and Hamiltonian is function on cotangent space, and actually quadratic in momenta, so P is momenta, XP is standard canonical coordinates in T star M. So we have, of course, in T star M symplectic form, and therefore it defines for us Hamiltonian system flow, right? That's actually whenever we project trajectories from T star M to M, it's going to be geodesics. Okay, so that's the Hamiltonian setup to study geodesics. And in order to do integration of dynamical systems, you would like to have kind of integrals, okay? And these are precisely Killing tensors in this language. So Killing tensor for the D is a homogeneous polynomial, so again, functional T star M, but which is homogeneous in momenta P of degree D. So you see P multiplied by itself D times. Okay, coefficients are just smooth functions on the base, and our condition for integrals that K and H commute. Okay, now K is polynomial of degree D, and if you look to Poisson bracket of second on of two polynomials of degree 2 and D in momenta, we get polynomial of degree D plus 1 in momenta. Okay, so this equation actually has more components than components of K, therefore it is overdetermined. Okay, and so and like previous here, I just told like it's basically like general, but I will keep in mind some sort of like overdetermined systems. So okay, so yes, it indeed overdetermined. So because that's number of unknown functions, and that's number of equations, right? So number of equations is bigger. And in fact, it's of course it's even finite type, right? So if you do prolongation, then actually we arrive to precisely the situation discussed in the previous slide. Okay, so yes, and yet we can prolong the system toward the D plus 1. There will be no compatibilities for the first D prolongations, and then closes to Frobenius system. Okay, so you get precisely compatibility condition on the level it becomes Frobenius. It's just first compatibility conditions, and you just have to check those and maybe later. But already at this step, you can see the maximal solution, the maximal space of solutions, right? Because it's linear system, right? It's linear PDE system, and therefore solutions will be of course linear space. And well, we can just look to it. And in the maximal case, that's the that's how solution looks like. I have to make some kind of warning. So in principle, when you look to Riemannian metric, you can think, well, it's just a representation of SO, right? But that equation is actually projectively invariant, and that's kind of also important point in parabolic geometry. Because the representation looks simpler actually in this case, and counting is simpler if you think about not a SOM representation, but actually SLM plus 1 representation. And that's the Young tableau. So it's second symmetric power of d-symmetric power of second skew power of actually extended space T star plus R in minus traces. Okay, yes, that's what I say, that E is projectively invariant. So we actually look to larger group. So the equations are invariant with respect to SLM plus 1. Note that what you can think like symmetry of space form, where there's like 3 different possibilities depending on curvature. This thing doesn't know actually about even if space form is positive curvature or negative or 0, it actually doesn't know about it. That system is will have like the same maximum amount of solutions. Okay, so now let's denote the space of Killing tensors, or D tensors, by QD. Well, I call them higher spins. Maybe it's not correct, but the kind of tensors with more indices. But like just like referring like to talk of Mike Eastwood, where we're conformal Killing tensors, right? Just would like to compare to this. Representation looks similar, but it's a position of different groups. in his case, it is SO group, right? Well, first of all, there's actually highest images of Blashian, right, which are bijective to symbols of those equations, and that's why conformal killing tensors. Yeah.
Symmetries.
Okay.
In T+1 dimensions.
Okay, thanks. Right, but even though like this, for conformal killings and for killings, they have common intersection by a smaller SO group, right? When you take biggest possible group for representation theory, where things become simple, the group becomes quite different. Okay, and in particular, counting is different. So here's the counting. So if we well, yeah, so here's actually the maximal possible dimension for QD. That's dimension of the previous Young tableau on the previous page. And this maximal dimension is achieved if and only if well, M has constant curvature. Okay, so if you take like sum of this all QD by all possible D, we get gradient Poisson algebra, and it's nice in flat case, well, in constant curvature case. Okay, in general, it's quite difficult to say, but okay, let's just say a couple of words still about the space form. Okay, so let me show actually for zero curvature how things look in coordinates. So Q1, well, you can read what the generators are. There's just actually killing fields, right? The usual symmetries of the metric. So PI gives you translations, and there's Rij actual rotations. And if you look to Q2, it's actually generated as a symmetric power of Q1. So you take all possible products. Okay, so you see Pi, Pj, and then you see products Rij and Pk, and also products of Rij and Rik, but they are not independent, actually. They are polynomial relations among them. And here I actually bookmark all possible polynomial relations. In particular, for this product of two small r's, you get something with 4 indices, and it behaves as curvature tensor. And yet, because if you remember the Young tableau, in this case, it will be actually box. Okay, so in fact, it would be easier in this case, of course, not to take Euclidean metric, but spherical metric, because then everything will be rotations and things will be uniformly, not split it into pieces. But if you would like to experiment with this, of course, you can do it, for example, through Lie, right? So here, what you do when you would like to see it in Lie. So you take second symmetric power of H2, okay, 0, 1, 0, 0, 0, it's H2, and this 2, it's second symmetric power, and you see it's split, right? And the thing we need is actually second summand, 0 to 0, 0, 0, and the other thing is what you project along, and what is this? That's wedge 4, and so projection to wedge 4 have to give you 0, that's called Bianchi identity, right? Okay, and then you look to third symmetric power, okay, so, and then you see the 3 summands, and the last one is the one which we need. That's precisely the Q3, right? But you have 2 projections, these both have to be 0. And that's the other identities which are imposed. So you actually can bookmark all possible relations in this way, but they become, of course, more and more complicated. And that's just flat story. Okay, if you go to curved stories, that actually not much is known. Things known about Q1, of course, it's just symmetry algebra, no restrictions on dimensions and so forth. But even about Q2, things are largely unknown, actually. Right. So, for example, what is the question? What is the next maximal dimension after the top one? That's not answered. Okay. So,
can you explain a bit what you mean? That it's not known? There are as many, no?
Well, because, yeah, so for example, the maximal dimension for Q2 is given, right? It's actually, well, not this one, but dimension of curvature tensors, right? What will be sub-maximal dimension, for instance? So if you take all possible metrics, but not space, but not of constant curvature.
I mean, by non-flat, you mean non-constant curve. Oh, that's what.
Sorry, yes, I confused because from this viewpoint, there's no difference between flat and constant curvature. Yeah. So it's kind of, yeah. Well, there are some results, but this is not complete. Okay, so now let me return to general story. So let's talk about symbols. So we have this function on jets. So you can think about it as a nonlinear differential operator indeed. Then it just is differential. And we don't give jets its usual differential on finite dimensional manifolds. So we get 1,4 on the same jets actually. One has to be careful because there's also called horizontal differential, and that actually traces the order. Now that's usual differential. Okay, what we do, we restrict this to fiber of projections from Lj to L minus Lj. If you remember, that's actually a fine space, so we know what it is. And because you kind of take tangent to the space, you actually can identify this proper vector space. Okay, so this thing is going to be homogeneous polynomial on cotangent space. Well, homogeneous of degree L. Well, I write this pi L star actually to pull back this cotangent space jets, but maybe I will just omit it later because it becomes confusing if you bookmark everything. Okay, so the symbol is just, as I said, homogeneous polynomial. We can write it as follows: we linearize our operator and we drop all lower order terms. Okay, leaving only the summation where length of multi-index alpha is L. Okay, so we get L vector. Okay, in this way, and that's called symbol. Okay, and we can also treat it as polynomial indeed on T star, and then what you do instead of writing derivative d alpha 1, d alpha and 2, and so forth, you just write the corresponding coordinate in momenta p alpha 1, p alpha 2, and so forth. It will be multiplication. Instead of multi-derivative, you get a product of coordinates of momenta, right? Kind of Fourier transform. You change differentiation to multiplication. Okay. Well, and the symbol actually is even though, well, I wrote some coordinate formulas as coordinate independent notion. Okay, so note if you take prolongation like differentiation, a total differentiation of operator and take symbol, it's the same as actually we do composition of symbol and the alpha. I can do interchange here actually. So it doesn't matter. This is multiplication sigma f and the alpha, that's commutative one, right? Because I just multiply polynomials. So if you see these coefficients, they are frozen. Okay, so you're not going to differentiate them. Okay, so when we do prolongation to order k, let's just unite all possible derivatives that we need, and then we take all their symbols, and let's define actually symbol of order k of our equation. Okay, that's going to be a linear subspace in a case symmetric power T star m. Equivalent is just prolongation of the previous symbol of order L. Okay, and that's when we go above our order of equation. If you go below, there's no restriction. So just put gk equal to everything. And if we have actually not one unknown function, but several one, it will be like something vector valued. So you tensor everything with corresponding vector space or tangent to this vector space if things are nonlinear. Okay, just small remark here. So if you, there's relation with other theories. So kind of this is like formal theory of PDEs coming from the works of Spencer and Sternberg, Guillemin, and Bott and many others, Quillen. They actually, what you can do, well, you can of course sum symbols, but it's just sum of vector spaces. But then you can actually take dual to this, and also take their sum, and that's a module over commutative algebra over, well, you take SKT, so symmetric power, general and strict symmetric power of T, or T where T is tangent to M at certain point. Okay, so so all possible symmetric vectors, right? And they act on this G star, because when we do dualization, actually errors are reversed. So GK is embedded into SKT star. When we do dualization, it's actually will be opposite direction. So SKT will act on G star. And well, the fact that it's actually a module comes from the prolongation property. Now, and this actually gives duality, because we talk about commutative algebra and modules, and this Castelnuovo-Mumford theory, this notion of regularity. And regularity was also discussed by Cartan when he talked about EDS, and that's the same story. This duality actually identifies those. Okay, so there's like regular sequence that's absolutely identical things. Okay, so how actually to check compatibility? Maybe now I come back to the question you asked. So if you have non-compatible, or we don't even know if compatible or determinate system, we have to check compatibility. So then we unite all the symbol spaces into Spencer delta complex. Okay, so if there's no restrictions, there's no equations, just remember this GI is just i's symmetric power of T star. And if you look to this complex, well, some people call it Weil complex. I would call it just the RAM complex of like polynomial. So differential forms polynomial values. Yes, so and that tells you what the differential is. That's called the delta differential, right? So if you do restriction, that it's still run as written. So you get a complex. And then if you have complex, a differential, you will define cohomology. Okay, that's called Spencer delta cohomology, and lower rank cohomology have meaning. So so basically we'll refer to second index is bi-graded, right? But second index is kind of tells you where in the complex you are, and the first tells you jet level, just order. So the zero cohomology count dependent variables. It can exist only by grading 0, 0. Otherwise, it's trivial. Usually people say that zero cohomology vanish. It's almost correct. So 0, 0 actually count dependent variables. First cohomology count equation. Usually people say first cohomology vanish. It's almost correct. Actually, they vanish in high range. But actually in the level of equations, they count your equation. And particularly comparing first and second, you can naively say whether the equation is overdetermined or underdetermined or determined. That's a naive approach still. And the most important, the second cohomology, which actually count compatibility conditions. And those you compute. If they actually vanish, again, they never vanish always, but like starting from order equation, for example, they can vanish. That would mean involutivity. But they may not vanish, but of course they will vanish if you prolong sufficiently, because all cohomologies are finite dimensional. So you have to arrive to the proper place. But that actually bookmark for you things you have to check. So if there will be compatibility, they will be sitting there, and you know how many actually conditions you have to check. And you even know actually, well, it's not just some vector space. It's you know what sits there, what these compatibility conditions are actually. Let's give you.
These are these really compatibility conditions, or would be, because it depends. It's just a principal symbol, but you still have.
Of course, yes. The same depends on
then you need to check if this thing.
That's where they live. That's where they live. In particular, if the space is 0, there's nothing to check, right? Yes, it can be that space is non-trivial, but actually abstraction is trivial. But yes, the compatibility sits there.
In which cases involutivity will mean compatibility?
Involutivity is kind of a technical definition. So usually people, for example, one of the definitions is full of equation has order L, and you have that second cohomology hi2 equal to 0 for I greater or equals than L. And if you can prolong for one step, then it's involutive. So you still have to check compatibility on one step. Right, but that's the case. So basically, it tells you that you have compatibility just constrained in one place, and if everything is the case, that system calls involutive. But otherwise, you can just prolong, and there can be compatibility or homology can be non-trivial in several places. Technically, then people say that you get involutivity from this place. But again, it's also confusion. Some people apply it as it's called compatible system involutive and so forth. Okay, so what happens if actually compatibility do not hold? In this case, some projection actually is not rejection. What does it mean? It actually means that you can differentiate your equation, take some relations, what's called differential synergies, and observe that, boom, the order of this relation drops from what you see by their symbols. And then you get new equation in your system, which will not be bookmarked by this going up process. And so you have to just add, and you have new equation of your system. It can be actually of higher order than original equations, of the same order, of lower order. Everything can happen here, but you have to restart. Okay, and you just take the new equation and you do things again. Okay. Okay, so and Well, actually, you stabilize. If you look to symbols, well, you have to stabilize because actually, so on the level of symbols, it's easy to see. It's a bit non-trivial to see on the level of equations. You need additional assumptions, for example, analytic. And so this procedure stops in finite number of steps. As Cartan formulated it, after some finite number of prolongations, you come to involutive systems or to contradiction, to equation 1 equal to 0. Right? As a theorem, it was kind of proved by Kuranische, so it's also a CK theorem. Okay, and on the level of algebra, you just say that you take differential closure. So you look to defining relations, and you start you just create a D module from it. You start acting by C differential operators from the left, and then you get involutive system with this. Okay, so let me tell about characteristic variety now, because that's important thing in counting. We can do general actually story here. So if you have operator, you take its whole prolongation, and then basically defines for you a map of jets, well, it's kind of decreasing order because differential operator, it needs to know more derivatives for the result. Okay, so that's equivalent to such a map from K plus L jets to K jets, and then prolongations actually equation gives this map for K equal to 0, and prolongations gives you for greater K. I kind of take more general context when both things are vector valued. So there are two bundles V and W. We may assume linear, not to right tangents everywhere. So symbol will be a homogeneous, well, symbol for K equal to L will be homogeneous polynomial of degree L, okay, on T star, with values in homomorphism V to W. Okay, so basically looking to for each component. So what is this matrix? So home V to W, it's space of matrices, right? And what will be actually entry in this? So well, rows will be linearization of every component of F, and then you take symbol of this thing. Okay, but since there are several unknown functions, that's actually you get not one piece but row, because you actually for each of those functions you have to do corresponding symbol. Okay, so what is a characteristic variety? So that's a polynomial on T star M, right, with values in home V to W. In overdetermined context, rank of W is greater than rank of V, and you expect like generically is injective. Also the same for determined. You expect generically is injective. So characteristic covectors are precisely those for which it breaks, of which rank actually drops. Okay, so that's degree L polynomial. So you have like you put covector T in L different places, and or you just say you take one covector, it's degree L polynomial with values in this matrix, and you write the equation rank less in general. Actually, for undetermined systems, it's kind of would be opposite, because rank of nu is greater than rank of V is greater than rank of W, right? So it's never injective, and this is from if you just apply this definition, so characteristics is everything. So it's better actually to modify and just say the rank drop, but I keep in mind overdetermined systems, so that's why I write this. And in particular, we can actually say strictly what is determined system, because there can be gauge equations and so forth, so it can be difficult to count. Just counting number of unknowns and number of equations doesn't tell you much actually, right? Because like Einstein equation, well, it's gauge invariant equation, so okay, in 4D, so it's 10 equations on 10 unknowns, like looks like determined system, but actually it's not. It's both undetermined and overdetermined. Okay, so if you compute characteristic variety for this, you get everything. So it's actually for determined system, if you have like V and W have the same rank, and then characteristic variety have to be just 4-dimensional one. It has to be a hypersurface. So that's proper definition of determined system. Right. Okay, now just if you don't want to think about jets and all this machinery, so you can think just about solutions. So you take a solution, then you can identify this lift of your manifold, right? Like graph of solution inside infinite jets. So it will be still m-dimensional sub-manifold. And then you say the characteristic variety is just bundle over this solution, well, which is just m-dimensional manifold. And yes, and this will be more or less given by the same formula, but you don't need to bookmark jets. Okay, so there's variation for characteristic variety. So as it here, because homogeneous polynomials, I can actually projectivize everything. So this comes as projective. We don't need to do it. We can have cone. Will be a fine characteristic variety. Sometimes we can do it over R. Sometimes we can do it over C. So both are important. For example, for definition of ellipticity, yes. So you need real characteristics, and for the count, which I will do next, I need actually complex characteristic, even though if system is real. Okay, so let me discuss now how we count dimensions of solution space. So we already made the evolution test and well to compatible system. So that's what I pass from E to E bar. Then actually we observe the following. So if for this system we start counting dimension of symbols, you take, for example, sum of all these dimensions up to the k, then this grows as polynomial in k. Okay, and you look to the top degree, and it's like k power d times coefficient c, and I drop the rest because the rest is not that important. Then actually these two numbers c and d have like invariant meaning, first of all, and second, well, they have names. In Cartan test, they called Cartan gender and Cartan integer. Okay, so and they actually mean the following. So if you look to a generality of solution, then general solution of the equation depends on C function of D variables. And so this D can be called functional dimension and C functional rank. Okay, the functional dimension, like how many arguments and then how many such functions do you need. Now, if you want to compute this can be done precisely through characteristic variety as follows. So let's take this previous symbol, right? Remember that's matrix, is sigma FD, okay? And when P is characteristic, that matrix has a drop in rank. So let's compute its kernel, just to check how much it drops. So call it kappa. So this D is actually dimension of characteristic of fine variety. Or if you would like to talk about projective, so dimension of projective variety +1. So we have to do everything over C because over R, some characteristic may just disappear. So this doesn't matter. This is analytic counting. Okay, and C will be a kappa-tized degree of geometric characteristic variety. So here I can think about projective and it's easier to compute, right? Or you can just take that it's actual degree counted with multiplicity, if you have your ideal. Okay, so let me show some examples. The first example is kind of a simple one, like everybody knows it, but discussion shows that there's some misunderstanding about it. So heat equation. Well, so if we just do the previous story, right? So there's the equation ut equal uxx, top derivative is uxx, right? We drop everything else, it's linear equation. So it's like dx square. And by doing this Fourier transform, which I said, we just change differentiation and multiplication, so it will be px squared. So p is covector, has two components, px and pt. Okay, so that's what? Well, that's line, right? So dimension of the line in a fine version is 1. Okay, d equal to 1, c equal to 2, because it's actually double line. It's counting multiplicity. So actually, general analytic solution depends on two functions of one argument. And this comes through actual general non-characteristic Cauchy data. You fix u at x equal to 0, function of t, and you fix ux at x equal to 0 to be some other function. This is a general function. And Cauchy-Kovalevsky theorem tells you that actually this general analytic phi and psi, you have a local solution, which will be also analytic. But that's not what people do actually. You know, heat equation is not solved like this. We actually teach it in school, right? And completely different. So you actually do characteristic data. Okay, so you say we fix u for t equal to 0, you get function phi of x, and so well. That's one function of one argument. So it has to be d equal to 1, c equal to 1. So something is wrong here, actually. Okay, well, actually, then if you look carefully to this analysis course, which we do discuss about heat equations, and you know that actually doesn't define flow. So for given Cauchy data, this phi of x, which is characteristic, you can go only to one side, with t greater than 0, right? And yeah, so this is semi-flow. You cannot predict past this heat equation. Okay, and that's not something that you do for analytic thing. That's a precisely smooth story. And this counting which I explained, that's very much analytic. So that's actually here completely different approaches. The first is analytic, the second is smooth. Well, it's not analytic, of course, yes, it's also far from this. Yes. Yeah. But just to appreciate a bit more, let me give you an example. So let's take such initial condition. Phi is equal to 1 over 1 minus x, okay? Near origin, it's nice function, okay, analytic function. Let's just do series expansion and we get for unique solution like this. So that's a solution which actually obviously diverges everywhere outside t equal to 0. So you can't extend it actually, right? Okay, so if you talk about counting, because analytics, so actually the first approach shall be used. One have to be a bit careful here with all the things. Okay, this was toy model. So let me take a bit more complicated equation. So here is the equation we obtained in joint work with Maciej Dunajski and Zhenya Ferapontov when we made gauge fixing of self-duality equation. Again, self-duality equation as given its diffeomorphism invariant, well, self-duality for, well, gravity for conformal structure. So it's diffeomorphism invariant, so there's huge gauge group, and if written like this, it's difficult actually to count. So you have to quotient out the gauge freedom. I will talk a bit more later in the second lecture how we actually quotient by some group actions. But in this particular case, it's gauge fiction, so we remove diffeomorphism freedom by, well, actually, I don't write anything here, but through this U and V functions enter into form for conformal metric in 4D, signature to 2. So, right, so what's here? So Q is operator of second order. It's, well, actually, C differential operator, what's called. You see coefficients actually depend on unknown functions and their derivatives. And the first two lines are actually two equations. So you have two unknowns, U and V, and you have two equations of third order. Okay, and well, okay, we have to do test. So here it is, we compute symbol, and the symbol have to be cubic polynomial in covector P. P has coordinates Px, Py, Pz, Pw, because that's x, y, z, w are independent variables. Okay, and first I compute symbol of Q. It's quadratic polynomial, as you see it below. Okay, and then I compute symbol of the equation. And if you look, the first equation, right? When I take its symbol, I get first line of my matrix. Okay, the first entry is linearization in U, right? And the second entry is linearization in V. But they depend only on the same momenta P, okay? So because this is taken from T star. Okay, so I get this matrix. So of course, I compute this determinant, and surprise, it's actually a perfect cube of this sigma QP. So actually characteristic variety is triple quadratic. And that's non-degenerate quadratic, that's actually important. And that actually tells you what is conformal structure. So this characteristic is precisely actually null cone of the conformal structure. Okay, so each solution UV gives you a actually, yeah. This you just go and read it off, because if you know null con, you know your conformal structure. It is self-dual. Okay, but just going back to the test. What do we see here? So we see hypersurface in R4, conic of hypersurface, right? So D equal to 3. And C is Is okay? Yes. Okay, thank you. I just write it in the simplest way, like Lie derivative of something equal to 0. Okay, yes. In some other cases, like if it's like a distribution, you have to write something is like proportional. And well, I don't want to go into technical details. I'll just write equation like this. Okay, and then basically that's your PDE system, and it's actually linear. In this way, it's much easier because it's just linear PDE system, and you're going to solve it. And for example, if you this is just if you look to if it's tensor, right? Then it will be just first order system. And well, then it's generated by by the symbol of the system will be just endomorphisms. And so what will be characteristic variety? Okay, so this will be such a covectors that multiply by something I in the symbol. And that's what's called rank 1 matrices. So this G has to contain rank 1 matrices. So the characteristic variety from the previous slide precisely corresponds to kind of support of rank 1 matrices. Well, because there's a tensor of the kind P tensor V, you just take covector part. There can be several vector parts indeed. Okay, and well, there's in the book of Sternberg, there's adapted version of what is this prolongation, and you can do the prolongation, and the statement is that prolongation's fine dimension of characteristic is trivial. That's general statement for general equations, actually, right? But this is particular for geometric structure, how it works. Okay, we can actually start with nonlinear equations for automorphisms, right? So that actually structure Q is preserved, so not infinitesimal version, but general version, then becomes nonlinear system, becomes a bit more complicated, but you can return to linear system by just doing linearization. And if you would like to do like formal study, compatibility, and so forth, that's done through Spencer delta complex, as I described. But if you would like to extend from infinitesimal version to local version, okay, then it's more complicated. You have to discuss Spencer decohomology. There was a series of papers by Goldschmidt and Spencer at the end of '60s, where they actually discuss this local problem. Or for example, if you know formal integrability of almost complex structure, there is actually local integrability, 9 heights equal to 0. That's complicated theorem. So that's over there. Yeah.
And how do you write these nonlinear equations of automorphisms? Just to get an idea.
Okay, so you have a metric, right? And just that you write the pullback of the metric. is metric itself, right? As quadratic equation for first jets.
You mean non-infinitesimal?
It's non-infinitesimal. Yes. Okay, so compatibility of the three equations in the case of geometric structure expressed with something which should be called curvatures, and that's the first thing which appear. Okay, and the maximal symmetry dimension corresponds to the flat Q. And the real question how to actually study possible dimensions of geometric structures, and usually you can kind of understand what is maximal dimension, and that's what I was discussing previously. So you know that the sum of symbols gives you maximal dimension, sum of dimensions of symbols gives you maximal dimension. But often there are some gaps, not all dimensions are realizable, and which are realizable is a very complicated problem. Like for Riemannian matrix, actually it was understood, three first gaps were understood. There's one gap, and then there's two dimensions allowed, then there's another gap, and then there's also three first gaps allowed can be understood. But in other geometries, it's already too complicated, and well, even the next dimensions called submaximal, it's already sometimes challenged. So, and there were some results due to work of Denis there, Henry Winter, Vladimir Matveev, Len Kozolabova, and myself in this direction. Okay, let me give some examples. Okay, and now I will talk just about finite type systems. So in this case, maximal dimension of solutions is just sum of symbols. It's actually finite sum, right? Because the GI becomes zero after some time. Okay, and of course, if system is kind of not flat, right, then dimension drops, so you don't get maximal. Okay, so let's start with conformal structure. So the bundle of conformal structures has this. It's like as to T star, maybe I have to restrict to cone, remove cone of the general structures, right? So for Riemannian one, usually write plus and that is 2, but for general I don't know. So I just leave it like this. Okay, so we write Lie equation for conformal structures, right? And then we see that the symbols, the first three will be non-zero. Note actually that I discuss here the index notation is in Spencer's theory. So if you use the parabolic, you have to shift it by 1 down. Okay, and instead of G0, 1, and 2, you get more symmetric minus 1, 0, and 1, which is actually proper for Lie algebras, but it's kind of would be unmotivated in the very general context. Okay, so the next one, so the prolongation started from 3 actually vanishes, and you sum dimensions, and you find the maximal dimensions, n plus 2 choose 2. So what we discuss here, so we get this Lie equation, but then there are parameters in it, which are actually components of conformal structure. And you would like to know, depending on those parameters, what is dimension or what is the dimension of the solution space of the Lie equation. So your parameters is functional family, right? And you would like to know what are possible dimensions. And maximal is easy, right? Is n plus 1 choose 2, it's so-called conformally flat case. The next one, well, yeah. 10 years ago, it was not known. So here it is. And yes, this is actually achieved on Einstein matrix, formal matrix. Okay, so if we take, for example, another matrix, but I will put restrictions, not arbitrary matrix now, but say, for example, Einstein matrix. Okay, so the bundle is the same as for matrix, just second symmetric power of the dimension space. However, I will do prolongations of this, and then actually I'm going to put second order restrictions in this equation. So now my functional parameter for the Lie equations will be those metric with differential constraints actually. And okay, and I would like to see so what are the maximal symmetry, and in this case the symbols, right, just like 0, 1, 0, and then vanish, and maximal is still of course flat metric or actually constant curvature metric, right? And the next one actually comes in here. So that's also a kind of computation which no, actually this one was known before the work with Denis. So that's one actually can be read off from the book of Yegorov in 70s. Okay. Yeah.
Are you also able to say how general, what's the generality of these submaximal Einstein that say how many of them, like how many parameters probably they depend on?
No, I don't think I can answer this. No. And I don't think it is contained in the work of Yegorov, which I actually referred to. No. Okay, and so we will be finishing soon. This ring, Bell's rings. But one more example. So I return to killing tensors, and I take this Q2, the kind of simplest beyond killing fields. So the scaling to tensors. So here it's actually kind of the same bundle, right? But I put equation that it's actually commute with Hamiltonian read from metric. The bounds, these are, well, that's behave in the same way. So it will be stabilization soon. But now I don't talk about the equation, right? I just to talk about equation for this thing to be killing tensor. Okay, and the maximal dimension is this. And you can again see it is a box, right? It's a space of curvature tensors. We discussed it already. But some maximal actually is unknown in this case. So the only thing I know actually is this lower bound. And I suspect it's actually sharp, but it was not proven. Okay, so that's kind of the first thing I would like to say in this lecture. Thank you for your attention.
Thank you very much for the lecture. Are there any further questions or comments?
So, Spencer equation. Okay, the Spencer approach to the equations. Actually, here you have the transitive equations, right? You do not have any restriction on the direction of vectors.
On what?
On the direction of vectors. They are transitive. Suppose you have a restriction, so there is a foliation with some structure. If you're looking at vectors which preserve this structure of foliation, then how this Spencer would look like?
I don't know that, why this is. So it's kind of equation plus inequalities, right?
Yeah, no, it's your restrictions on the vectors. Right?
So that's inequalities, right?
Okay, yes.
I think like Gromov considered it actually, this was important when he talked in the book differential relations, right? He actually does things like this. He, however, wants this equation to be, well, have certain algebraic structure in order for his RH principle to work. I would say the Spencer theory doesn't tell anything about it. Of course, you have to still just omit all these inequalities and run the compatibility test, but it doesn't tell you anything about solution, right? Well, just like stepping away from equations, talking about geometry, you know, Rashevsky-Schwarz theorem, it tells you that you have, if the distribution is holonomic, then you can go from any point to another. Now put inequalities, it becomes difficult to unsolve problem. Instead of saying you have distribution, put cones inside and prohibit your motion. Does that sound something similar to what you're asking, actually?